When an aircraft is flying, it's basically dealing with a few invisible players pulling and pushing on it. First, we have got gravity. That's the weight pulling the plane down. Then the engines step in to create thrust, pushing the plane forward. And of course, the air itself pushes back, creating what we call aerodynamic forces. Now, here's where things get interesting. The big challenge in aerodynamics isn't just figuring out how much force the air creates, but also where exactly that force acts on the aircraft. That what matters a lot because it affects the aircraft balance and stability. So what's really happening? As the plane slices through the sky, it forces air to move around it. This motion sets up stresses in the air, and according to Newton's third law, you know, the one about every action having an equal and opposite reaction. Those stresses push it right back on the aircraft. These stresses come in two flavors: pressure stresses and viscous stresses. When we add them all up across the surface of the plane, we got the total aerodynamic forces and the moment that goes with it. And that, in a nutshell, is the heart of aerodynamics. Back in the 1800s, John Stringfellow had to put wing model on top of fast-moving trains just to measure aerodynamic forces. Today, we have much better options. We can put a model in a wind tunnel, hold it still, and blow air past it. Or we can use computers to simulate the airflow and calculate the forces right on the model. Of course, it's not always perfect. Things like the wall of the wind tunnel or the resolution of the computer grid can affect the results. But this approach saves a ton of time and effort. Now, let's talk about coordinate systems. When we describe an aircraft's motion, we actually have a few options for how to set up our frame of reference. For example, we could use a geocentric system based on latitude, longitude, and altitude, or use a fancy mathematical system tied to the aircraft velocity, curvature, and torsion, or the most common one, a system that's fixed to the aircraft itself, moving and rotating right along with it. And that's usually the one we go with an aerodynamics, but here's the thing, no matter which system you choose, the actual physics doesn't change. So how do we set up this aircraft fixed system? Well, most planes are almost perfectly symmetrical. If you cut them down the middle, left side mirrors the right. That symmetry helps us define our axis. The x-axis runs along the body of the aircraft, pointing backward in the direction of flight. The y-axis points upward, and the z-axis points out to the left wing. Together, these three axes form what we call the right-handed coordinate system, and once this system is locked in, it becomes our reference for describing forces, motions, and pretty much everything else about the aircraft aerodynamics. Alright, let's break down how aerodynamic forces act on an aircraft in simple cases. Because of symmetry, the total aerodynamic force usually lies right in the plane of symmetry of the aircraft. And here's the fun part, we can split this force into components in two different ways. The first way is the classic one you have probably heard of, drag and lift. Drag, which always point opposite to the aircraft motion, basically resisting the forward speed. Lift, which acts at a right angle to the direction of motion, keeping the aircraft up. So in this case, the total aerodynamic force A equals lift plus drag. But there's another way to look at it using Cartesian components. Here we just break A into AX and AY. AX, the longitudinal component along the aircraft body, and AY, the normal component acting at the right angle to that line. Now, here's something important to remember. When we talk about the x-axis of the aircraft, it runs along the reference line of the plane, pointing backward. That doesn't always match what we think of as horizontal, relative to the ground. It's all about the aircraft's own frame of reference. The main goal of aerodynamics is simple. We want to predict the aerodynamic force, that is lift and drag. But what can we say about these forces without knowing all the details of the airflow around the airplane? Let's make some simple assumptions. The plane is flying straight and steady. The air around the plane stretches out to infinity and is undistributed far away. So what do we need to actually solve the problem? The shape and geometry of the airplane, the speed and direction of the airplane, or equivalently the air moving past it. The properties of the air itself, like density and viscosity. These 3 points are exactly what we will explore in the upcoming videos. Thank you for watching and see you in the next video.